Start recording now. I am hoping this is recording everything correctly. Okay, at first I'm going to do a very brief review of something. It should be open, right? It should be open. Just open the door. Okay, okay. Well, this is a good way to start off the video. So people know the quality of students at U of T. They can't open a door. That's fine. Okay, so right now I'm going to do a kind of brief review, which will be maybe a little bit. I think I talked about this last time, but then I'll say the same thing again, but faster. And then we're going to talk about something new, which I thought would be a review for people who took Math 247, but apparently this semester Math 247 started with something else, so it will not be a review, but we will be pretending like we're reviewing this, and that we already all know this. Okay, but first we'll do some actual review, right? If I say we're going to do review again, then there has to be at least some part that's review, right? I can't completely lie to you. So let's do. Yes. Okay. So let's do the following definition. So I'll just define again what a matrix is, because we talked about it last time, and I will actually have like bonus suggested exercises about understanding what a matrix is in terms of like a linear, in terms of it being a representation of a linear map. But those will be like optional for people who haven't seen it before. There will be some very simple trivial calculations. Like once you understand what's going on, it will be like 5 lines for you. But if you don't understand what's going on, then you should do the exercise. So it is like 5 lines for you. Okay, so definition. So let's T be a linear map from V to W, be a linear map with the dimension of V and dimension of W being, finite, less than infinity. So there's some finite number. Okay. Then let's say alpha, some vectors u1 up to vm be a basis of v. Let beta some, let's say w1 up to wn be basis of w. Okay. Now I will define a matrix. So we now define a matrix. So I will use the following notation: M alpha beta of t. So alpha means the input basis is alpha, the output basis is beta. Okay? This is what this notation means. And we'll see in a second why this notation is so good and why we should all be using it. Okay, to be a numbers, to be numbers arranged in an m by n grid. Numbers numbers arranged in an n by m grid, where the entry in the ith row j column is given by, and it is given by, so I'm going to write, okay, so Cij, I will define this to be the ijth entry of the matrix. So instead of having to write this, I just write Cij. I'm just, introducing a new notation. I'm very lazy. I don't want to write this each time. Where, it is given by T of, let's actually write this in like red or something because this is important. T of Vj is equal to C1j F1 plus dot 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 plus Cij Fi plus dot 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 plus Cnj Fn. Okay. So the entries in the matrix are the expansion coefficients of TVJ in the beta basis. So the expansion coefficients tell you if I take something in the alpha basis, send it forward by the map T, and then expand it in the beta basis. How does that look like? Okay. Also, you watched the video. Were there any like random cutouts or no? Or was it smooth? Okay, perfect. So then when this computer shuts down, I know it's still recording. Actually, sorry, let me just very quickly hit the settings so that it doesn't, see if I can like, yeah. So screen blank, let's say never. Beautiful, okay. Yes?
Are the F's supposed to be W's? Yeah.
Oh yes, my bad, sorry. F are supposed to be W's, yes. Good point. Because I think I used F last time, and so I'm using F this time, but W makes a lot more sense. Sorry. Okay. So now, okay, this is a great, a great thing to write down. But if you write this down, that means you have to think about it. But let's try and draw this in such a way that you don't need to think about it as much. So let's we have that definition over there. Now let's draw what an actual matrix looks like and think about how to interpret it. And then once I talk about it briefly, we can move on to newer and better things that we have not seen before yet. Okay. So suppose I have my matrix here. Okay. This has, row 1 up to row n, and this has column 1 up to column m. Do you agree? Okay. And the entries in here are the Cij entries, right? So this is C11, Cn1, Cnm, C1m, okay, and so on and so forth. You have some numbers, and they are arranged in a grid, right? Very easy to understand. But okay, what do these Cij mean? So I said that J is the column, right? Yes, the column. So J is like this. And I'm saying that the numbers are, TVJ, we're expanding the vector Vj. And you're taking Vj, we're taking T of it. So we're taking Vj, sending it to W using T, and then we're expanding it in the W basis, in the beta basis. Okay, so what does this mean? This means that, okay, so let's use this for V and this for W. So this is alpha, and then blue is going to be for beta. Okay. This means that, okay, if you look at this column, right? This column is telling me, okay, if I take Vj and shove it into my linear map, right, I'm going to get as an output TVJ. And what this tells me is that, okay, out here, I'm going to have my W, okay, W1 is going to be V1. So VI, VM, W1, WJ, WN, right? Good. So what this is telling me is, if I plug in vector V1 into my linear map, then on the output, I'm going to have this column is going to give me the coefficient in front of W1, the coefficient in front of W2, the coefficient in front of WJ, the coefficient in front of WN in the expansion of TV1 in the W basis. Right? Do people kind of see what this is, like what I'm getting at? So the column, right? The column tells you the ith. Wait, I want it to be the other way. I'm sorry. This should be j and that should be I. Okay, I keep making this. This should be j, and then this should be I. Right? So the row is the coefficient in front, tells you the coefficients in front of wi, and the column tells you which of the v's we're expanding. Okay? So the column vector tells you the expansion of tvj in the w basis. Right? So if I do t of v1, that's going to be c11 w1 plus c21 w2 plus c31 w3 and so on and so forth. So that's how you should read it. Like I'm inputting vectors v and I'm outputting this way vectors w. Okay? Yes?
And also to clarify, the Vj is just, it has to be part of the basis of V.
Yes. So the whenever I say v, in this case I'm saying I have a basis alpha, and all these v's are just some basis vectors of v. And that's why you can see that a matrix, whenever you write down a matrix, you are kind of always talking about, a matrix always has some basis that it's in. It has some input basis and it has some output basis, right? Because suppose I chose a different basis for alpha or for beta, this matrix would look different. But it would represent the same linear map, right? So whenever you're talking about a linear map, or a matrix of a linear map, that always has some choice of basis associated with it. And usually it's implicit and it's clear what basis you're choosing. But sometimes the basis that you chose is special, and maybe you need to specify that. Okay, that's good. Now, the other comment I will make, and this will be on the kind of suggested exercise. Well, this is going to be the bonus suggested exercise for next time. Is people? How many? Raise your hand if you know how to multiply two matrices together. Yes. Okay, great. So the point is that matrix multiplication was defined specifically for the reason that if you had say operator t, not operator, linear map t from v to w, and you had some linear map s from w to u, right? And okay, you had some basis alpha, beta, gamma. So this is the basis for v, this is the basis for w, and this is the basis for u. Then matrix multiplication was defined in such a way that the matrix of from alpha to gamma of s composed with t. So you do t first, then s. So that's why it should be a matrix going from the alpha basis to the gamma basis. So the basis of v to the basis of u should be equal to matrix beta gamma of s, matrix multiplication, matrix of alpha beta t. Right? So you specifically define matrix multiplication to have this property, that the product of the product of the product of two of the representation of two the product of representations of matrix representations of two linear maps is equal to the representation of their composition. Right? So you can see that this is composition of linear operators, but this is matrix multiplication, right? So the way you define the way you define multiplication of matrices such that this is satisfied. Okay. And okay, there'll be an exercise about this that's fairly straightforward for you to think about why this is a point that kind of matters. But the point that does matter is whenever you kind of are multiplying matrices, and why I like this notation so much is you want your input basis to be the same. So if you're multiplying two matrices together, you want this matrix to be outputting stuff in the same basis as this takes input in, right? Because your basis is kind of like your language, your coordinates. If I'm giving you some output in like a certain kind of coordinate system, but you don't take input in that coordinate system, then you can't do anything with my output. Do you agree? And so here's a point about the change of basis. This will be also a comment I'll make later. Is okay. Suppose I have a matrix of something that starts in some basis alpha and outputs in some basis beta. But suppose I had information in some other basis alpha prime, right? So the information that I want to plug into here is written, I have it written in a different basis. So the question is, what is, this equal to? Can someone tell me, if I know this, how can I find this? So, how can I change the input basis? Yes?
You would have another u that you're multiplying it by, and that one has alpha prime, alpha prime as the input and alpha as the output.
Of what?
Mm-hmm.
What is this matrix?
Wait, are we still doing the S and T things?
No, I'm now doing so this was an aside about matrix multiplication being a thing, and so now we know this. So my question is, suppose I give you this matrix, so I tell you what the matrix that represents T is in the alpha going to beta basis. But then suppose I give you another basis alpha prime. How is this matrix related to this matrix in this new input basis? So what do I have to do? I have to, okay, sure, in the back.
My answer isn't too far from what she said, but essentially you have to take the matrix from alpha to beta with T, and then outside of that you just create another matrix from alpha prime to alpha.
Yeah, so that's the right idea. So what we're saying is, okay, this takes input in some alpha, in coordinates with some that are called alpha, in some alpha coordinates. Let's just call them alpha. Okay, they use some coordinates, but we have data in a different coordinate system. So what we want to do is we want to take the data we have in our coordinate system and then transform it into the coordinate system that we want, right? So I'm saying we know how to take in alpha, right? We know how to compute stuff using the alpha coordinates. But now I want to compute stuff with the alpha prime coordinates. So what I want to do is I want to take my alpha coordinates, convert that into, I have something, suppose I'm given something in alpha prime coordinates. I want to first convert that to alpha coordinates and then just do this, yes? So if I want to write down a matrix that takes alpha prime as input, then I should just multiply this matrix by something that converts alpha prime coordinates to alpha coordinates, right? But at the same time, I want this to be, I don't want to actually change what the data is, right? I want to have it be, the exact same vectors, but I don't want to change the information that's in them. So this should be, what's an example of a linear map that doesn't, exactly, the identity. So we'll multiply this by a matrix of the identity, but we'll write the matrix of the identity in a weird way, with the input being in the alpha prime and the output basis being in the alpha. So this will maybe not be a matrix that is, it's not going to be a 1 1 1 1 1 1 1, right? This matrix will look maybe weird in some way. However, this matrix will definitely, this will take your alpha prime coordinates, convert them into alpha coordinates, and then we can plug this into the matrix that we already had. And that's why I like this notation, is to check if you're doing the right thing. All you have to do is see, okay, are the adjacent coordinates the same, right? Okay, this kind of makes sense, vaguely. I'll have an exercise about it. You'll do the exercise, you'll understand. We will not need this until in maybe an hour. So you should think about this, and then we'll do an exercise. Okay, but overall, people understand the idea that the coefficients inside a matrix are just taking T of a basis vector and expanding it in the target space basis. That makes sense, yes? Okay, that's the important thing. This other stuff is also really important, but okay, we'll talk about it later. But yeah, all the change of basis is just taking the same data and rewriting it in different coordinates. Okay. I've spoken about that for like 20 minutes already. That's insane. All right. So I will actually, I don't want to erase this. And I don't want to erase this either. What's more important? I'll erase this. Okay. So now we'll actually start talking about the new and interesting thing. Review. We'll talk about something completely new, or as I call it, we're going to do some more reviewing. So before, we had just a vector space, right? And the vector space had its structure where you had some vectors, you can add them, you can scale them, okay, and that was it. But now, eventually we want to do quantum mechanics. And quantum mechanics is a little bit more complicated than just vectors. There's more stuff to it. Otherwise it'd be too simple. So, we're going to now define an inner product. So definition. An inner product on some vector space. Is that visible? Yes. On some vector space V, could be potentially infinite dimensional, is. Can someone guess what it's going to be?
Multiplying vectors together?
So a vector space, an inner product is going to be a what kind of object? Not a functional, it's just going to be a function. A functional is, I guess, something vaguely different. But okay, sorry, why did you turn off? I thought I told you to never go blank. Okay, that's fine. So okay, is a function. A function. And we will denote this function in this funky way with these brackets with the dots. Okay, and it's going to go from V cross V into the field. In our case, the field is always the real or complex numbers. It is never anything else. So, real or complex numbers. Okay, so, and this function is going to have the following properties. Let's see if I can remember them. So, property 1. This function is going to be linear in the first entry. So v plus u plus lambda u w. No, let's not do w yet. V plus u, I don't know. What's another good? Yeah, fine. W. No. Let's do. There's w. What else is there? G, H. No. Okay, G. So v plus lambda u g, with g is equal to inner product v with g plus lambda inner product u with g. Okay, so in the first entry it's linear. So yeah, it's a function that takes in two vectors. You have two entries for these two vectors. Okay, and it's linear in the first entry. Do you agree? Yes.
Is that like multilinear?
It's not going to be quite multilinear. It will be close to being multilinear, but it won't be.
Okay.
And there will be an important reason for that, and we'll talk about why. Yeah, so it's not a tensor.
It's only in the first entry, so that's why it's not.
It's in the first entry. In the second entry, it's skew symmetric. We'll see what that is in a second. Okay. The next thing is I think that's called positive definiteness or something. Doesn't matter. The point is that V is always greater than or equal to 0. Okay? And VV is equal to 0 if and only if v itself is 0. Okay? That makes sense? And let's see. Right, these are, sorry, I just want to double check that there's one more. Okay, so I just kind of wrote 2 in one go, okay. Maybe actually, let's write these as separate ones. Let's have this one as the first one, is greater than 0 for all d, and then the third one will be VV is 0 if and only if V is 0. And the fourth one is going to be that V inner product with U is going to be equal to the complex conjugate of U inner product with V.
Forgot what that is.
Complex conjugate?
Yeah.
Do people not remember what
It's
complex
when you do
conjugate
a
is?
plus versus a minus.
Yes. So if I have a complex number, so review of review, if you have a complex number a plus bi, and you take the complex conjugate of that, that's a minus bi.
Okay.
So you just flip the sign in front of the part in front of the I. Okay. So and this is what you were saying about it being linear or not. Because of this, it doesn't actually end up being linear in the second entry. And we'll see in a second why. And if the field was the real numbers, right? If the field was the real numbers, then this conjugate doesn't matter, because if you take the conjugate of a real number, it stays the same. So if this is an inner product over the real numbers, then it is in fact linear in both entries.
What is a conjugate of a real number?
Well, okay, you do the same thing. You write your real number as a plus bi.
But there is no I.
Exactly.
B is 0.
B is 0. You said b to
talked
0.
about that, but okay.
Yes, yes. I agree, but it's the usual thing that you would expect. Okay, so a conjugate, this is a key point. If you take a conjugate of a complex number, sometimes people just write a bar over it. Sometimes people write like a plus bi and write like a star over it in the corner of the number. There are many different notations, and some of them then start conflicting with each other and you get confused. So I will try and stick to the bar notation, I think. I will try and stick to the bar notation, but I can make no promises. So if you're unsure like what a star means, you should ask, because stars are used in different contexts. Like later we're going to have adjoint operators, and I'm going to use a star, but then people who took 240 with me, remember that I used stars to mean like the dual map, but okay, that's not going to be the same thing, and we will learn about that in a moment. Okay. So do people see? It's a function that takes in two vectors. It's linear in the first entry. If you plug in the same vector, it's always something greater than or equal to 0. And in fact, if you plug in the same vector and you get 0, then you know that that vector has to be 0. And okay, it has this thing where if you swap the entries, and this is, I guess, for all UV, if you swap the entries, then you get the complex conjugate of what you had before. Okay? Yes, makes sense? So let's look. Should I be always writing on this board, or do you want me to write on that board as well? I don't know. I'm giving preferential treatment to one board over another. Can I move this? Well, but then people can't see in the back. Is that? Yeah, I guess you can see that. Okay. So let's first prove, I guess, one property. There's many properties, but we'll prove one. So the property is as follows. So properties. There's many more. You can read Axler to really do all of them, but almost all of them are like just trivial things. This is the one that's kind of interesting to me, or maybe I'm forgetting something. Maybe it's not the only important one. But but this is what I can remember off the top of my head. Is so the first property that we'll prove is that V lambda U is equal to lambda bar V comma U. So this is the complex conjugate of lambda.
I have a question.
Yes.
So the function takes a Cartesian product, so two vectors in a pair,
Yes.
and it takes it to an element of the field that the
Yes.
vector space is over.
Yes.
Okay.
Yes. Yeah. R or C. Okay. Good. So okay, how do we prove this? Well, it's very easy to prove this. Oh, actually, wait. So this proof requires a fact, another fact that should be remembered. So maybe I'll go back to the review. I'll box it in green. Another thing that you should know about the complex numbers, about taking conjugates of complex numbers, if you multiply two complex numbers and take the conjugate of the whole thing, that's actually equal to taking a complex number, taking the conjugate, and multiplying that by the conjugate of this other number. So this is something where you can just take a plus bi times c plus di and just multiply it out and see that left side equals to right side. Just believe me that if you take a conjugate of a product, that's equal to the product of the conjugates. Yes, this bit makes sense. Okay, and that's why that whole thing works. That's what that proof is really based on. Proof. Okay, if I do v comma lambda u, this is kind of almost like linearity, right? It's like almost like I just took out the lambda, but it got an extra conjugate, so it's almost like linearity. So we should use linearity somewhere. But where do we have linearity? We have linearity in the first entry. Yes? So how do I make lambda u get into the first entry?
Use the fourth property.
Yes. So with the fourth property, I know that I can swap the order, but then that turns it into a conjugate. Yes? People see that? So this should be equal to lambda uv, but conjugate of this whole number. Do you agree? Now, I have what? I have this lambda here, and now now it's in the first entry. I can use linearity in the first entry, right? And I can take it out. Do you agree? So I have conjugate of lambda times u comma v. So u inner product v. Okay, right? But now I can use this fact I told you just about complex numbers. The conjugate of the product of two complex numbers is the product of the conjugates. So this is lambda bar times u inner product v bar. Yes, do you agree? And now this is uv. I can swap it back using the fourth condition again, right? And I get lambda bar v comma u. Okay. People agree with this, yes?
I have a question.
Yes.
Is the field always R or C?
Yes, in our case, always R or C.
Okay.
And I don't think it would make too much sense. It would be very hard to define this for something that's not R or C, because then, what does it mean to be greater than or equal to 0? Right? And,
You
Sounds
can't really
okay.
have complex numbers greater or equal to 0 because it's not ordered.
well, yes,
You have
how?
to take the magnitude of the complex number.
No, in this case, actually, you have that v comma v always has to be real. I guess, is that a
You get it
postulate?
From the third,
Yeah.
fourth property.
Yes, you get it from the fourth property, yes. Yes, you get from the fourth property actually that v comma v always has to be real. Why? Because if, so this is, I guess, another fact about complex numbers. Okay, if z is equal to z bar, that means that it must be real. Why is that the case? Because if I have a plus bi is equal to a minus bi, that means that b has to be 0. Right? But if b is 0, then it's a real number. And so now, if you look at the third postulate, I have v comma v. Well, that should be equal to v comma v. But v comma v is the same thing as like swapping them. That does nothing. But swapping them should give me a bar. So you get v comma v should be equal to v comma v bar. So that means that v inner product v has to be a real number. Do people see that? No, you look confused.
I got lost a bit. What do you
Okay.
just said?
So Do you agree? Did you understand this part? If a number is equal to its own complex conjugate, it has to be real, because that means a minus bi is equal to a plus bi, and so b has to be 0. Okay. Now let's look at v inner product v. V inner product v. If I swap the v's, nothing changes. But according to the fourth rule, if I swap any two vectors, I should get a complex conjugate. So v inner product v should be equal to v inner product v bar of that, because switching doesn't do anything, but that's also equal like that. So you get that this number should be equal to conjugate of itself,
Okay.
meaning that it has to be real. Yes. So you get that this is always a real number, even if it's into the complex field, which is going to be important in a bit, in a second. Okay. And so now, in a similar way that we did this, we have a second property. And the second property is going to be as follows. V u plus w is equal to vu plus vw. And here you don't have, the proof is exact same. Does anyone want to try and prove this? You will be on video. It's your chance to make your YouTube debut. Yes. Yes, go ahead.
I'm going to see if I can even start this.
You should just do the same thing that was done before you. And then, okay. So you want to use these 4 properties, right?
Oh, well, using the first postulate, we know that.
Can you use the first postulate?
We need to use the first one and the fourth one. I
Okay.
think.
So which one? Okay, what are you doing
So
first?
first we're gonna make this into u plus w, and then v.
Yes. And then bar, right?
Yeah.
Okay. So that's you use the fourth condition.
Yeah.
Yeah.
And this equals to, and then I assume you can, if it's a.
It's a sum. So yeah. The sum of two conjugates is equal to the conjugate of the sum. Yes.
Alright, so then it's going to be u v plus w v,
Yes.
which then equals to
Okay. And now you just unswap them.
v u plus v w.
Okay. Yeah, that's it.
Therefore,
And therefore you conclude the result. Okay. Perfect. Yes, and of course doing a conjugate twice does nothing, because that means you flipped this to the thing in front of the b to a minus sign, and then you flipped it back, so you got a positive again. So that doesn't, doing a conjugate twice doesn't do anything. Okay. Okay, people understand these two properties. So it's like almost linear. It's linear in the first entry, but it's almost linear in the second entry. The difference is when you pull out a number, you pull out the complex conjugate of it instead of the number itself. So it's skew symmetric. It's almost linear.
Oh.
Do you
Okay,
see?
Yeah.
Because now I had a lambda here. I pulled it out, but what I pulled out was a lambda bar.
So you could add these two properties together into one, which just has the scalar as a conjugate after. Like you could combine them. You know how you usually just get the job done of linearity by
Yeah.
combining addition and multiplication? You could do the same thing here, right? Except just.
Yeah, I could do it.
But to
I'm
make
just
it more obvious.
yeah, I just made it more obvious. Yes. So I could write something like v u plus lambda w is equal to vu plus lambda bar vw. Okay, I could write that down. Okay, but this way I write this down and then you're confused and have like 1 minute to think while I'm explaining it. This way I write out the same thing twice and you have double the time to think about what I'm saying. Okay? That's all there is to that. Okay. This makes sense. So we define this thing called an inner product. And now, if you have a vector space with an inner product structure on it, we call that an inner product space. Okay. So, I guess definition, inner product space is a vector space with plus inner product. A vector space with inner product. Okay. Let me think about this. Now we're going to define yet another thing. Okay, so this is good. Yes, I can move on with this. And also, people haven't seen this before. This is now new, right? Okay. So we might be here for a little bit longer than we were last time. Because, yes, hopefully no one has to go until maybe about like 6:59 or something like that. Because if we're meeting once every 2 weeks, I don't want to give you like too many exercises, but also I don't want to like, not get to quantum mechanics at all. And it's not like, the other thing is that I want to preface, so what we defined linear in first entry, and then like, what was it, complex linear or some skew symmetric, whatever, there's like 20 different names for it. But it's not quite linear in the second entry, right? However, when physicists do inner products, they usually define it the opposite way. It's linear in the second entry and skew symmetric in the first entry. And so at some point we'll start like switching between the two interchangeably, but it will be clear from context if you pay attention. So that's okay. Sorry. Surely it will be clear from context. Sorry, I needed to add that caveat. Okay. So that was good. Where's my green chalk? Oh, it's in my hand. Okay. So now let's maybe switch colors to add something. Now we're going to define a new thing. We're going to define a norm. Actually, no, I'll still use one. We're going to define a norm. So, definition. So, a norm on a vector space. Vector space is a norm on a vector space is a
Function?
yes, it's a function. Is a function that takes in a vector space and outputs a real number. Now it's always a real number, never a complex number. Exactly. We're just going to define what a length is on a vector space. So the first thing that it's going to do is, okay, first of all, you want the norm to always be positive, right? Second thing, you always want the norm. You want the norm to be 0 if and only if the vector is 0, right? You don't want to have non-zero vectors with 0 length. And option 3, the third thing we want is, you want the usual thing that you always want. You want the triangle inequality. Why is this the triangle? Why is this called the triangle inequality? Do people know?
Yes.
Yes. Why?
Because if you draw a triangle, if you add together two of the sides, that's always more than whatever the third side
Yeah, exactly.
is.
So let's draw a picture. I love pictures. So let's draw a vector v, and let's draw a vector u. Okay, v plus u. Okay. Now, what can I do? Okay, I can take this vector, translate it to here. Do you agree? This is going to be vector u. And so the sum of v plus u is going to be this vector. This is v plus u. Do you agree? And the point is that the triangle inequality, if you're just doing usual Euclidean geometry, you can prove that, okay, this side length plus this side length always has to be bigger than this third side length. And this is kind of an important fact. And so essentially what we're trying to do is we're trying to give a generalized notion of what it means to be a length. based on kind of like what we see in like R2, what we can observe in the real world, right? This is what we observe in the real world, and so let's try and give a generalized notion. And so now you can define a notion of length on any vector space. Well, in principle.
Over R though, right? Can you do
No.
length over C?
Yeah, why not? If you have, look, this is a function. It's just some function that takes in a vector, outputs a real number, right? I can always define a function that takes in a vector, outputs a real number, hopefully.
Oh, true. But the
Right?
norm itself has to be.
The norm itself has to be real, but you can define a norm on vector spaces, not necessarily over R.
Okay.
In fact, we're about to show an example of a norm, and it's not really an example in the sense that it's still abstract. But see, before I talked about this inner product stuff, and now I'm talking about a norm. Surely there is some relation. Do you agree? Yes? So, surely there's some relation. What is the relation? So, I guess this is like a theorem or something. I don't know, is that still kind of visible what I'm... Yeah, that's kind of visible. So, okay, theorem. No, I'll write this theorem in green. Theorem. How do we show this? Okay, theorem is let V be an inner product space. So it's a vector space equipped with an inner product. Define, okay, wait. Then the following is a metric. Wait, not a metric. Then the following is a norm. A metric is, I guess, a metric is a bit different. The following is a norm. Okay. V is equal to the square root of the inner product of V with V. Is that visible? Kind of. So this is V, the norm of V is equal to the square root of the inner product of V and V. Okay? So, yeah. The point is that the inner product defines you some kind of norm for free. Okay, so let's look at the proof. Okay, well, let's look at the first two conditions. The first condition is that the norm of V is always greater than or equal to 0. Okay, well, let's look at this formula. I have inner product of V with V. According to the definition of an inner product, that's always greater than 0. If I take a square root of that, that's still always greater than or equal to 0. So you're automatically satisfied with this. Okay, good. Second one is V is equal to 0 if and only if the norm of V is equal to 0 if and only if V is 0. Well, in the conditions for the inner product, we said that V inner product V is 0 if and only if V is 0. Okay, so then if I plug V into here, this number is 0 if and only if V is 0. And if you take a square root, okay, that means the square root of that number is, okay. So 2 is also already satisfied. 3. 3 is a little bit more difficult. And actually, this time. Okay. It's perfect. Me making a mistake got cut out. All right. Yes, all right. Oh. Does it need to use... Oh, it uses the... sorry, let me see. Triangle inequality. Okay, so I have not... Okay, good. Okay. We can still do this. This is fine. Okay, now, so this is the norm of U squared plus the norm of V squared. Do you agree? And now, what is this? This is VU, wait, sorry, not, yeah. Now what is left? What is left is this term and this term. So this is UV, U inner product V plus V inner product U, right? But this is the complex conjugate of this. So this is like I'm taking A plus BI plus A minus BI, right? So the complex part cancels out. So this should be really be plus 2 times the real part of U inner product V. Do you agree? Okay. Now I think I'm about to use a result which we actually haven't proven entirely. But actually no, this is fine. This is fine. Is it fine? Yes. We needed to prove the Cauchy-Schwarz inequality. Okay, this will first. I didn't realize that. Okay, this is going to be one of the important suggested exercises, because I didn't want to talk about it now, but okay. So this is the statement. The statement is that this is called the Cauchy-Schwarz inequality. This is incredibly important. So this is this. Okay. The statement is if you take an inner product of a vector with another vector and take the absolute value of that number. So the absolute value means you do a squared plus b squared square root of a complex number.
What if the what's it called? The inner product thing is complex.
Yeah, so you take the absolute value.
Well, what if it's an I?
Yeah, so the absolute value. Oh, right. Sorry, you guys don't know what an absolute value of a complex number is. I was not expecting that. Sorry. This is worse prepared than I thought it would be. Okay, if you have a plus bi and you take the absolute value of that, that's like saying, that's defined as this. The absolute value of a plus bi is the square root of a squared plus b squared. By definition. Or you can think of it, so the absolute value of z is equal to the square root of z times z bar. You can check that this is the same. Right? Because difference of squares. You'd have a plus bi times a minus bi. And by difference of squares, you'd have a squared minus bi all squared. But I squared gives you plus. So it'd be a squared plus b squared. Okay. So you have this inequality. This is an incredibly important inequality. And shame on me for trying to skip the proof of it. But I would rather have you do it in as an exercise, because it'd be maybe better to get accommodated with stuff. Okay, but then, so from this, if we have this inequality, and you know that the total magnitude of uv has to be less than the magnitude of u times the magnitude of v, then I can write the following. I can say that this whole thing is less than or equal to u squared plus v squared, the magnitude of v squared, plus 2 times the magnitude of u times the magnitude of v. No, too many lines here. I need one more here. Okay? So 2 times the real part of this number. If I take, the statement here is 2 times the real number would be 2 times a. Like if this number is a plus bi, this would be 2 times a. But a should definitely be less than a times b. Or what am I saying? No. Is that what I'm saying? Yes. No, sorry. A should be less than a squared plus b squared square root. That's what I'm saying. Yes. A should be less than a squared plus b squared square root of that. And so I can replace this with then this being less than this. Okay. But this, can someone notice? So if you didn't get this step, that's fine. You can understand it later. Can someone tell me what this looks like?
It looks like u plus b
Yes. It looks like the magnitude of u plus the magnitude of v all squared. Okay, but what did we just show? We showed that the magnitude of u plus v all squared is less than or equal to the magnitude of u plus the magnitude of v squared. Since these are positive numbers, I can take the square root of both sides and conclude that it has triangle inequality. So conclude. Okay, this step with the Cauchy-Schwarz inequality, very important. You will do it. Okay, so don't worry about it. But the important big picture idea is, if you have an inner product, it gives you a norm, where the norm tells you, lets you compute the length of the vector. Okay, that's fine. Now the following question is: can we go the other way? If I have a norm, do you necessarily always have an inner product? That is not the case. And so, okay, I will not explain. Well, I will not explain in too much detail why. But the question is geometrically. What does the inner product tell us geometrically? And that's the next part. And we're going to talk a little bit about linear independence, and maybe we'll take a tiny break, and then we'll see how long we continue for. Okay. So, let's look at an example of an inner product, and then use that as motivation. So suppose you have R2. R2, that's our vector space. Then I can define the following inner product. So inner product between xy and AB. I will define this to be x times A and y times x times A plus y times B. So I multiply the x coordinates together, I multiply the y coordinates together, add it. Okay, you can check that this indeed satisfies all of these axioms of being an inner product. Okay? Yes? Okay. But can someone remind me what was the kind of special formula about this inner product? What was this equal to? This is probably something you learned in high school in terms of these as vectors. So if I drew this vector as xy and this vector as AB, what did the inner product of these two vectors mean?
Dot product?
Yes, the dot product. Exactly. This is just the dot product. That's exactly what I wrote down. But do people remember what this was related to?
It's related to both of their lengths times sine.
Times, yes, cos. It was cos, right?
Yeah, sine is for the cross.
Yeah.
Yes. So, if I look at this, right, then this would give me what? This would give me the magnitude of xy times the magnitude of AB times the angle between them. Okay, now if you think about the inner product as just some function, right? Well, okay, if I have a function, then I can compute all of these norms, right? Because I said that the norm comes from the inner product, right? And you can actually check that these norms are in fact the same as that norm defined from this inner product. Okay. But now this means that if you tell me what the inner product is, then okay, I can compute this with the inner product, I can compute this with the inner product, I can also compute this with the inner product. This means that somehow the inner product is telling me something about the angle between these two vectors. Do you agree? So this is kind of the additional thing of what's different between the inner product and the norm. The norm only tells you stuff about the lengths of vectors, right? And that's why, you see, a norm only takes in one input, right? It can only tell you something about one vector. An inner product lets you kind of compare two vectors and in some sense has something about like the angle between these two vectors, how they're oriented relative to each other, in some sense. And we'll explore this in more greater detail. So this is kind of the R2 analogy. Okay? Right. Do you want a short break now or a short break later? Oh, I can't pause the recording. I mean, I can like stitch two videos together. That's okay. Maybe now? Okay. Okay, I'll stop recording. I will start recording. Okay. So now this will be relevant for the first question of your suggested exercises. And okay, I guess, yes, this will be relevant for the first question of your suggested exercises, but not immediately relevant as to what we're going to do now. I will erase this. If that's okay. Hopefully everyone got that down. And now we are going to talk about.
I have a question.
Yes.
When you give the example of v equals r squared, are you just defining the inner product as x dot a?
Yes,
y
I'm
dot
saying
b?
let's define the inner product to be that.
Because it satisfies the properties?
Yes, and you can check that this satisfies those properties.
Okay.
Yes, that's it. I gave you an example. This is an example of an inner product.
Is it unique?
No.
Up to your rescaling?
Well, no, because I can do like a change of basis or something and do something weird there.
So you can define an inner product differently and it's still in R2? Is that the question?
Yes, you can define like this. An inner product is just some function with some properties. Surely there's more than one function that does this.
Yes.
Yes.
But do they always give the vibes of a dot product?
Yeah, I mean they always give you these exact vibes. They always give you these exact vibes. They always give you a norm. They always satisfy the Cauchy-Schwarz-Bunyakovsky inequality, and all the usual fun, exciting stuff. So everything that we prove, they will do, because everything we prove is like stems from this. Okay. I will actually. Okay, I will now use this board again, so it's better on the video. Okay. Now we're going to actually start talking about. We're going to go back to last week. What did we talk about last week? A bunch. What did we start off by talking about? Linear independence. So we're going to try and see how an inner product helps us with linear independence. So okay. Definition. Yet another definition, guys. Vectors v and u are orthogonal. Are called orthogonal. Sorry. Are called orthogonal if u inner product v is equal to 0. Okay? And why is this called orthogonal? Maybe from your high school math class, you may remember that if you had some two vectors and they were perpendicular to each other, then their dot product would be 0, and you would get that they're orthogonal. How do you see that their dot product would be 0? Remember the formula that we wrote? That the dot product in R2 specifically, like the x times x plus y times y, that one. This is u times v times cos of the angle between them, but cos of 1 is 0. So cos of 90 is 0. So if you had two vectors that are perpendicular to each other, that would be, that would be 0. So this is kind of also modeling on R2 and how R2 works. Yes? I can erase this example. So yeah, this definition kind of follows that. So in some sense, when you have two perpendicular vectors, what would be the natural guess to, oh, that does not look perpendicular at all. Okay, like this. There we go. That makes sense. What am I trying to do? If you have two vectors that are perpendicular to each other, what should you probably be able to say about their about their dependence on each other?
Not dependent on
Yeah, they should be linearly independent from each other, right? Okay. And in some sense that they should be completely linearly independent from each other, right? Okay. Well, let's check the case to first double check that they have to be two vectors have to be linearly independent from each other. Okay. how to check that? Okay, well, so quick lemma. So uv equals 0 implies that u is linearly independent from v, and here I'm assuming that neither u or v are equal to 0 themselves, because otherwise, okay, 0 inner product something else will always be 0, and you can prove that yourself.
But you said that it's if and only if v is.
No. So I said v inner product itself is 0 if and only if it's 0. But if I plug in another vector,
Oh,
a
okay.
different vector, then this can be 0. So this is a good point. So it's v and v is v inner product v is 0 if and only if v is 0. But if I do a different vector, then that can be anything else. And that's why this Cauchy-Schwarz inequality was significant. Why I had to take the absolute value of it, right? Because you could have a vector inner product, another vector could be a positive number, negative number, complex number, whatever you like. Yes? Okay. Well, suppose the contradiction, you do this by contradiction. By contradiction. If u and v were linearly dependent, that would mean that u is equal to some lambda v. Do you agree? Then inner product u v would be equal to u lambda v. Would be lambda v v would equal to lambda v comma v. Okay, which therefore is 0 if and only if v 0. Okay, but I said let's assume u and v are not 0. So okay, it's if and only v 0 or lambda is equal to 0. Okay, but that means then u is equal to 0 because u is equal to lambda v. So okay, if two non-zero vectors are orthogonal to each other, then they have to be linearly independent. Yes?
Is that lambda VV?
Lambda VV, and this is also lambda VV. This is UV, and I said suppose they're linearly dependent. If they're linearly independent, then U equals to lambda V. Okay. Yes? Yes? Okay. 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 Then we will have the next statement. So the next level. Let some v1 up to vn, let's say, be a set of mutually orthogonal vectors. Mutually orthogonal vectors, meaning that the inner product of vi with vj is equal to 0 for I not equal to j. So if you take any two vectors, you take the inner product between them, it's 0. Okay. So if I have these vectors, then what do we expect to be true? That all of these vectors are linearly independent. So then v1 up to vn are linearly independent. Yes? Okay. Okay, I'm going to keep this up still. I don't have enough boards. Yeah, that should be written on like the very backboard. But what I have written on the very backboard is this. Okay, I don't think we'll get to this at the end, so I'll erase all of this for now. I was too ambitious. I'm sorry. Okay, so let's prove that statement that we wrote earlier. So the statement that we wrote earlier was what? You have some vectors v1 up to vn, and that vi inner product vj is equal to 0 for I not equal to j. And we want to show that this implies linear independence. Yes? Yes. How did we define linear independence last time? Yes?
If you take out a vector of a set,
Yep.
it's not going to be like spanning the same set because this vector is not.
Yes,
independent.
that's right.
You need this vector.
Yes, but good. But we also is not. Sorry. Yes, that's right. But sorry, we want to show that these are linearly independent. So let's go by contradiction. So sorry, that was right. But so go by contradiction. Contradiction. So suppose they are dependent. Okay, and if these vectors are dependent, then what can I do?
Present one vector as a linear combination of others.
Exactly. Good. So this means exists I such that Vi is equal to the sum of other vectors, AK, Vk, and it's k such that k is not equal to I. So I can present this vector as a linear combination of all the other ones that aren't it. Yes? Yes. Okay. So now what can I do? Now, how's this proof going to go? I'm going to essentially try and show that the inner product of this vector is going to be non-zero with some other vector, and that's going to give me a contradiction. Yes? So in some sense, I'm going to show that there's going to be some piece. So what I'm going to show is essentially that Vi will actually, if Vi is in some sense can be written as a combination of the other vectors, then it has to have some piece of this other vector inside of it, right? But orthogonality kind of tells you that there's completely no pieces of any Vi in any other Vj. Okay, but that's me saying something abstract and unreasonable for now. Okay, so how do we prove this? Okay, so this means, so take k such that ak is not equal to 0. So something that actually take a vector vk that actually contributes to Vi. Yes? Then we take the inner product of Vi with Vk. I can replace, let's take k prime. Yeah, k prime. So fix a k prime. This inner product of the vector Vi with this vector k prime, I can replace Vi with this expansion. Yes? This is the sum of ak vk. K is not equal to I with vk prime. Right? This is just one of the vectors in the expansion that actually contributes to this expansion. Do you agree? Now I can use linearity in the first entry, right? And I can pull the sum and the coefficients outside. Vk with vk prime. And this is I is not equal to k is not equal to I. Do you agree? Okay, but vk and vk prime, what is this equal to? What is vk and vk prime always equal to? By assumption, right? We're looking at a set of vectors which are all mutually orthogonal. So if k is not equal to k prime, it has to be 0. So I'm left with only one piece in my term, which is ak prime, vk prime, vk prime. Vk prime inner product vk prime, because the only thing that's left non-zero is, by this assumption, the vk prime, and vk prime inner product vk prime is always, not zero as long as vk prime is not zero. And okay, we assume this is not zero. Okay, good. But okay, this is non-zero by assumption. Well, yeah, by the definition of an inner product. This is non-zero by assumption, so this is not zero. Do you agree? But what was this whole thing we were computing? We're computing the inner product between Vi and another vk prime, and by assumption it was 0. So we showed that if all the inner products are pairwise, we said, okay, suppose all the inner products are pairwise 0. And we said, suppose that the vectors were in fact linearly dependent after that. And we showed that assuming linear dependence gives you contradiction to the inner product between any two vectors being 0. So meaning that contradiction, and all the VKs, VIs have to be linearly independent. V1 up to Vn is linearly independent. Right? So the inner product here, it kind of told you that, kind of tells you, is there a piece of Vi? The camera light keeps going down, so I don't know if it actually like keeps recording or stops recording. I have no idea. So you might have a very choppy video where it's like missing half the stuff. Yes?
I think I missed how you took out AK prime, how you went from this.
From this to here or from here to here?
From the first thing.
Here to here.
Yeah.
Okay. We assume that all the vectors are pairwise orthogonal. So if you take any two different vectors, the inner product between them is 0. So here I'm summing over k, and this k prime is some fixed vector. Right? This is 0 if k and k prime are if vk and vk prime are different vectors, and this is some positive number if vk prime and vk prime are the same vector. So in the sum, the only bit that contributes is vk prime and vk prime, because all the other inner products are just 0 by assumption, because we said let's look at some vectors which are all mutually orthogonal to each other. Yes?
I got lost.
So
If I have a sum, if I add up 0 plus 0 plus 0 plus 1 plus 0 plus 0, I can ignore everything that's 0. Do you agree?
Yes.
This is a sum just like that, where vk inner product vk prime, this has to be 0 for any vector that's not the same as vk prime, right? The sum is over k, so I'm changing this vector. This vector stays fixed, right? And we assumed that all of the vectors are orthogonal to each other. So this is 0 for any choice of vector that's not vk prime. Do you agree? So I'm just adding up a bunch of things which are 0, except for the vk prime with vk prime.
Okay.
Does that make
That
sense?
makes sense, yes.
Yes?
Thank you.
Like we just
Okay,
assumed that the
yes.
inner product between two different vectors is 0. I'm saying here's a set of vectors where the inner product between them is any two vectors is 0. So you're left with only one thing in the term. Okay, and this has to be non-zero, but that gives you a contradiction. So the main point is, if you have a bunch of vectors which are all pairwise orthogonal, then they have to be linearly independent. So all of a sudden, somehow, this inner product thing captures something about linear independence in this way, about orthogonality. And in fact, it gives you kind of a stronger condition for linear independence, because you could have two vectors that are linearly independent, but the inner product between them is still non-zero. For example, like in R2, like I said, if you have two vectors like this, they're linearly independent, but there is a non-zero angle between them. So the length of this times the length of this times the cos angle between them is not going to be 0. So this is kind of a stronger condition than linear independence. So that's good. But okay, what do I want now? So I found that, okay, if I have some orthogonal vectors and they're all orthogonal to each other, then they're linearly independent. What do I want to do now? Before we defined linear independence, and then what did we do with it? We made a basis. Exactly. And so now what we want to do is we want to define an orthonormal basis of our vector space. Is that good? Is it okay if I erase this? Do people remember what an inner product is well enough by now? Surely we will be done soon.
How much more do we have to go?
Great question.
It is 6:40.
Yeah, I'll try and wrap up by 7. What I wanted to do was too much. It was completely unreasonable. Okay, definition. A basis is called orthonormal. Orthonormal if, so a basis in this case is going to be some v1 up to vn, right? Like usual. And it's going to be defined orthonormal if what? If. So the norm of vi, so which is the square root of, vi, inner product vi, is equal to 1. So this is the kind of the normal condition, that all the vectors are normalized to have length 1. And the inner, and guess what's the next thing?
And they're orthogonal.
All orthogonal to each other. So vi vj is equal to 0 for all I not equal to j. Do you agree? So this is what an orthonormal basis is. Well, why is this useful? This kind of lets us differentiate between a basis like this versus a basis like this. So before we would allow something like this to be a basis, but an orthonormal basis can't be like this. An orthonormal basis always looks like this. It's always perpendicular in R2, right? So in some sense, the vectors are like completely independent of each other, whatever that may mean. I don't know. So right, so these two vectors, they're perpendicular to each other.
So,
Yes.
So now you just have to show that that spans the vector space, but not that it's linearly independent.
No.
'Cause it's-
Not necessarily. I'm telling you, a basis is called orthonormal. So I'm telling you, this is already a basis.
Okay.
Let v1 up to vn be a basis.
Mhm.
I will call it if it's a basis, I will call it an orthonormal basis if it has this
Okay.
additional condition.
Okay.
Yeah.
Yeah.
So it's like assume this already spans the vector space. Yes.
So the inner products, like the notion of inner product is completely independent from that of a basis?
The notion of an inner product is yes, completely independent, right? Because we had a basis before we had inner products, right? This is just like if I have an inner product, then I can look at special kinds of bases, which are maybe more interesting.
So we don't need a basis to find inner product. It's just like it's a property of the space itself.
What is a
Inner
property?
products.
No. An inner product is if you have a vector space, you have to give it an inner product, right? An inner product is some additional function,
Okay.
right? You have to give it a function.
Okay.
Yes.
So. Okay. Yes.
Yes.
Right.
And so an orthonormal basis is you had a basis before, and now there's some special kinds of bases which work extra nicely with the inner product.
Okay.
I have a question.
Yes.
Is orthogonal only defined based on inner products always? Because I feel like I've heard that for even in 240.
Well, in 240, I think whenever you talked about it, it was like you were using something that is an inner product. You just didn't call it an inner product.
Okay.
Yes.
Okay.
Okay. Although I don't know, maybe there's some other context where you call, like, you have the same word used in math for like 20 different things always. So it's like, okay, is this word used in some other context? Most likely. This fly is not at all responding to me. That's not a healthy looking fly. Okay.
It's a common chalk dust.
I think I had that one.
Yes,
before.
I'll move the chalk away from it. Okay. So now the question you should be asking is like, okay, well, if I had a finite dimensional vector space, I always had a basis, right? Because by definition of a finite dimensional vector space. Suppose I gave this finite dimensional vector space an inner product. What's the question that you should then ask with this definition? Does there necessarily exist? Yes, right? Because right now, we know that finite dimensional vector spaces by definition have a basis. Okay, I define this to be like, oh, if I have an inner product, then some of the bases are somehow special and we call them orthonormal. Okay, but what if there are just no such bases at all? then why are we making this definition? So let's show that in fact, if I have a basis, I can kind of do something to it and turn it into an orthonormal basis. Okay? So theorem. And this theorem is like theorem. Let V1 up to Vn be a basis. The statement is, then exists an orthonormal basis E1 up to En such that, this is important, the span of V1 up to Vj is equal to the span of E1 up to Ej. So the idea is I can take this basis, right? And I can do something to it, deform it in some way, to turn it into an orthonormal basis. But not only that, such that, if I take the first three vectors here, and then the first three vectors in the new basis, then they still span the same vector space. So it's kind of, and this will kind of tell you that we're going to do this by induction. We're going to take the first two vectors, turn them into an orthonormal basis. So like construct the orthonormal basis out of the first two vectors. Then we're going to add another vector, then turn that into an orthonormal basis, add another vector, and just kind of do this step by step. Okay? So now, let's draw a picture yet again. And we're going to draw the same picture that I drew over the break and talked about. Okay. Suppose I have a vector v and I have a vector u. Do you agree? Yes. So let's choose one of them. So let's take vector u, right? Then I can always scale it down to be a unit vector, right? I can scale it down such that this has length 1 and call this E1. Do you agree? Yes? Then, what can I do? I can take the vector v, and I can say, okay, well, how does E1 fit into it, right? Let me think about what I'm about to say. Yes. I can realize that this vector v is actually something. This vector v is actually some scalar multiple of E1 plus this other orthogonal projection. Do you agree? So this is vector v. This is E1. This is going to be vector some lambda E1, right? And so this vector is going to be v minus lambda E1. And then I can divide it by its length to give it length of 1. And we'll define this to be the second vector. So the procedure that we're going to try and do is we're going to take, start with two vectors, choose one of them, and give it the length unit 1, right? And then kind of subtract a certain portion of this vector from the other vector to only leave the bit that's orthogonal to it.
I have a cube. Is this always in R2?
These pictures, the pictures that I draw are always in R2 because it's a blackboard.
Yeah, I guess so. So this concept applies to all R.
So this picture that I drew applies to R2. In principle, it applies to Rn. But then, the geometric idea that I'm describing. But when I actually prove it, we will prove it completely generally for any inner product space.
Okay.
But this is like a picture for how to think about it.
So for complex and real vector spaces.
Yes, for any inner product space has the factor. Right. In the theorem statement, I didn't specify. So let V be a basis of an inner product space V of a finite dimensional. Well, I mean it's obvious. Inner product space V. Okay. See, it's just too many words to write.
I wrote inverse V as well.
Yeah, exactly. It's too many words to write. Okay, do people see the idea that we're going to be doing? We're going to take a vector and then kind of subtract everything except for the orthogonal bit from the other vector and kind of keep doing that. Okay? So, this board doesn't move. Okay. So, that's how we're going to... And this is called the Gram-Schmidt procedure. So this theorem you can call the Gram-Schmidt theorem or the Gram-Schmidt procedure, whatever it is. So Gram-Schmidt. No, do it in this color. I think it's called Gram-Schmidt like this. I don't remember. There's many things I don't remember. Okay. Yes?
No, that's good.
Oh, that's good. Okay. So, okay, suppose let's start with proceed by induction. Start with say, well actually, yeah, let's just have so v1 up to vn. I'll write single, and then I think we'll do this, and then we will almost stop here. Okay. So I will define E1 to be I will define E1 to be V1 divided by the norm of V1. Okay? You should believe me that this is an... Oh, I forgot another condition for the norm at the very beginning.
We didn't even prove it then. Like when we did something about inner product spaces.
There was one condition for the norm. Oh, this is bad on the video. That's okay. The other condition for the norm, write this in your notes. Lambda V is lambda, right. You want this. If you scale a vector by lambda, then its norm should be scaled by lambda. Which is what you would expect, but okay, it's pretty bad that I forgot that. I don't know if I can like write something in the video like, oh, I forgot a thing. Sorry. That's pretty important. But this is something you should be able to prove quite easily yourself. Okay, I'll put it as an exercise as well. Okay, but yes, I'm sorry, this is... But you know, you kind of expect this. If I scale my vector by lambda, then its length should be scaled by lambda. Yes, no surprises there. Okay. That is still very, very hard to see. You guys will not be able to like see anything because of my laptop, but that's okay. That's fine. That can hang on like that. Okay, can you guys kind of see what's...
Yeah.
Okay. Okay, so I'll define the first vector like this. Okay? Then I'll define the second vector to be, is going to be V2 minus the inner product of u of V2 with E1 divided by the norm of this of itself.
I have a question. I don't know what V2 is. Why did you get that?
We have vectors V1 up to Vn.
Yeah.
And so these are given. This is a basis or whatever. Okay? So I define E1 to be V1 divided by the norm of V1. Do you agree?
Yes.
Then E2 is going to be V2, I got it from this list, minus V2 inner product E1, E1's from here, times the vector E1. So this is a scalar, this is a vector. Yes? Divided by the norm. So, now I'm going to define E3. E3 is going to be V3 minus V3 E1 minus V3 E2 E2 and divided by the norm of of the thing that's in the numerator. And you kind of keep going like this, where EI is going to be VI minus the sum of VI EJ. J. I should have proven a different thing first, but that's okay. Sorry, this is I, this is J up to I minus 1. Okay, and when I just kind of write a norm like this with a dot in the center in the bottom of the fraction, I mean just divide by the norm of the thing up top. Okay?
Why are you doing this with the e's? Why are you defining them like this?
Great question. So, one way that you could do it is you could just like take this formula for EI, take another formula for EJ, compute the norms, and get explicitly that you get 0. Like you if you wanted to, you could do EI inner product EJ, expand that out like before using just the rules, and get that it's 0 and that these guys are orthogonal, and you can clearly see that these are orthonormal, have unit length 1, because I'm taking a vector and then dividing it by its own norm, right? Okay. One thing that you want to be careful is you want to be careful that you don't divide by 0, right? But surely you won't divide by 0. Why? Because, okay, the norm of a vector is 0 if and only if the vector itself is 0. Yes? And the other thing is that, if this was 0, this means this was equal to this. But all the EJs are defined in terms of previous V's, right? So this means VI would be some linear combination of other VI's. And so they wouldn't be linearly independent, so you get a contradiction. So you know that this is always non-zero, and so that you can divide by the norm, and that's okay.
Wait, you said that if you're taking the inner product of a vector, it's 0 if and only if the vector is 0, but that's only for if it's the same vector that you're inputting twice.
Yes. Yes.
Are you inputting
This is the norm.
vector
The norm.
values?
The norm. I'm saying
Oh.
this is the norm. The norm is the inner product of the vector with itself, square root.
Okay, thank you.
Yes. Yeah, so I'm dividing by the norm here. Okay. So why does this work? This is really this plan in action, right? If E1, remember what we said. We said that the inner product, let's do it like this. We said in R2, like the idea comes from R2. The inner product of U with V is the length of U times the length of V times cos theta. Do you agree? Yes? Times cos theta, right? So if this is 90 degrees, if I draw this perpendicular, right? Then this is really just V times the length of V. So this length is V times cos theta. Do you agree? This bit is the length of V times cos theta. Right? If this is theta, this is theta. This is theta, then this bit is V cos theta. People agree? Yes. Trigonometry. Easy. Now I want to take V and subtract this part from it, so I'm only left with this orthogonal vector. Do you agree? E1 has length 1. 2. And I got something that is perpendicular to V1. Then I normalized it, and then I normalized it to be orthonormal. Then I went to E3. I took the third vector, subtracted everything that's parallel to E1, subtracted everything that's parallel to E2, normalized it. Then I went to the next vector, subtracted everything parallel to all the previous vectors we've defined, and then normalized it, and I keep going like this. Okay. And so my claim is that the vectors ei inner product ej is equal to 0 if I is not equal to j, and 1 otherwise. I will not prove this immediately right now, but you will prove this on like an exercise. But it's really not that hard. You will just like plug this formula and then plug in a different j into it, and then just show that everything actually cancels, and you get 0. Like you can just compute this. But as long as you see the geometric picture, you're kind of taking a vector and subtracting off everything parallel to the direction e1, and subtracting off everything parallel to the direction e2, and you're left with something that's perpendicular to e1 and e2. Does that make sense? The idea you're trying to do is trying to subtract everything parallel to e1 and e2, and you're left with something perpendicular to that. Yes? Okay, and I have one final comment. And then we'll finish. We will finally finish. Okay. Actually, let me see if I actually just did this correctly. What if everything I told you is just wrong? Because I'm being guided by this. Yes, everything I told you is in fact correct. Good. Okay. And now, final comment. Final theorem. Sorry. Yes. Okay, final theorem, and then we're done. I'm sorry this is taking so long. Where's my clock?
It's over there.
Oh, okay. Exciting. Okay, final theorem. I'm really not doing the best of jobs with drawing pictures for you right now. I feel like my picture game could be better, but this is what you get. Okay, so this is kind of not really a theorem. This is more of a computation. So computation / theorem. Let, I don't know, v1 to vn be an orthonormal set of vectors. Orthonormal set of vectors versus orthonormal basis is a basis has to span an orthonormal set, doesn't have to span, but otherwise they're all pairwise, orthogonal, whatever. So let u equal to, let u be in the span of v1 up to vn. Agree? Yeah, that's okay. See ya. We're almost done anyway, so you're not missing much. Let u be in the span of v1 up to vn. Okay. Then u is equal to the sum of u inner product vi. Sorry. I'll instead of v1, let's do e1 up to en. So that v is just for a basis and e is more for orthonormal bases. Okay. Okay. Yes? So what this is saying is that the inner product of u with all of these orthonormal basis vectors actually gives you the coefficient of u in the expansion in front of ei. And this, I should have really done this first before showing you the Gram-Schmidt procedure. That would have made more sense. I kind of forgot. I got too caught up. So let's prove this.
So is this span vn for v1, vn, or u1?
This is u ei.
Above that should be span 1 through
e1. Yes, sorry. e1 en. Yeah, thank you. So proof. Okay, proof. So since u is in the span of e1 en, then surely E has to be equal to some sum of some AIs, EIs, right? No. Surely there have to exist some AIs, by definition, yes? Okay. But then, I can do what? Okay. Let's then look at the inner product of U with EI. Right? Makes sense as a thing to look at. U inner product EI. Yes? Well, I can look at what? I can look at this. U is, I can just plug this in. EI. Inner product EI. Now, remember, I have linearity in the first entry. Can people not see that well? I can move this. Is this better? Okay. I have linearity in the first entry. I can pull out the sum and the factors. Oh, sorry. This is bad. Let me use J. Sorry, I'm messing up everything here. So this is the sum over J, so I'm not using the same index for two different things. So this is EAJ, EJ, EI. Sum is over J equals 1 up to F. Okay, sorry. Do you agree? Okay. This makes sense. So I said, okay, I want to prove that this is equal. I said, okay, if U is in the span of E1 up to the n, then surely I can, write it as some linear combination of these EIs, right? Okay, but then let's take U and take the inner product of U with EI, with some fixed EI. Okay, well then, what does this tell me? I can plug in the expansion for U in here. I can bring out the sum, right? But okay, remember, I'm summing over the inner product of all EJs with a fixed EI. Do you agree? EJ, inner product EI, is what? Yes, it's 0 if I is not equal to J. So I can essentially ignore every term that's not equal of J not being equal to I, because that's just 0, right? So this is going to give me AI, inner product EI with EI. Okay, but this is an orthonormal set, right? Meaning that EI inner product EI is what? 1. So this is equal to AI. So I just showed that U inner product EI is equal to AI. Do you agree? And so that essentially proves this, right? Because then if I plug in U inner product EI instead of AI, I just get this expression. Okay, so what does this tell us? This tells us that if I choose an orthonormal basis, right, then the inner product of a vector with one of those orthonormal basis vectors just gives you the coefficient in the expansion of U, right? So if I take any vector, the inner product of the vector with an orthonormal vector gives you kind of the piece that's in the direction of EI. Okay, but notice here it was very important that this is an orthonormal set of vectors. Both the ortho, so the orthogonality, and the normal part were used in this proof. Right, so if you just had an arbitrary set of vectors like this, it is not necessarily true that the inner product tells you how much of this vector is inside of this one or the opposite. This is a way of thinking specifically if you have an orthonormal basis where everything's perpendicular to each other. The inner product tells you how much of this basis vector there is in this vector. Okay, and this will be very, very useful when we start talking about something next week. Okay, I'm sorry this took very long, but I think right now we've gotten through almost everything that I could have wanted, so that next week we can maybe even start talking about quantum mechanics a little bit, tiny bit. Okay. And I'll try and post these videos.